In this video, we're going to study VSEPR theory and predicting molecular geometry.
Well, should we say prayers first?
Here are your learning targets. Draw correct Lewis structures, identify electron domains, and determine the electron domain geometry and molecular geometry using VSEPR. So here are some things that we have to remember. Number one is valence electron. So we said that valence electrons are the outermost electrons of an atom, and they are the ones involved in bonding. To look for the valence electron, we look at the group number for the main group elements. For example, hydrogen is in group 1A. It has 1 valence electron. Beryllium in 2A, 2 valence electron. Nitrogen is in 5A, so it has 5 valence electrons. One exception is helium. Helium has 2 valence electron because it doesn't follow the octet, but it follows the duet rule. We also talked about Lewis symbols. So here, each valence electron is shown as a dot around the element symbol. So for example, oxygen. Oxygen is in group 6A, so it has 6 valence electrons. So you draw it like this. 1, 2, 3, 4, 5, 6. We put the electrons one at a time because it follows the Hund's rule. Another example is chlorine. Chlorine is in 7A, so that's 1, 2, 3, 4, 5, 6, 7. So these dots show the potential bonding sites because again, valence electrons are the bonding electrons. Now let's talk about the VSEPR theory, or what we call the valence shell electron pair repulsion theory. So this predicts the molecular shape by assuming that electron groups around a central atom repel each other and spread out as far apart as possible to minimize repulsion. So that's the goal of the VSEPR. Because remember, in a bond, we have electrons. Because as we all know, if we have like charges, they will repel each other. One thing that you should know is the electron domain. When we say electron domain, it refers to any region around a central atom where electrons are likely to be found. So it can be a single bond, double bond, triple bond, or a lone pair. These are electron domains, and they count as 1, okay? Regardless if it's a double bond or a triple bond, you count them as 1. You also need to know the AXE notation because this is usually used in textbooks. AXE notation is just a way of writing VSEPR shapes. A will be your central atom. X is the number of bonding domains, or basically your bonds. E is the number of lone pairs on the central atom. Now I will present a table showing the different molecular geometry. So this is the VSEPR table. It's basically a summary of the molecular geometry. In the first column, you will see the number of electron groups. Again, this is the regions of electron density around the central atom. That's the total number. Here you will see the number of bonds. Here you will see the lone pairs. Lone pairs are unshared electron pairs sitting on the center atom. Here you will see the AXE notation. Electron pair geometry is the arrangement of all electron groups. So that's bonding plus the lone pairs. Now here's what we want, is a molecular geometry. It's the actual shape of the molecule considering atoms, not the lone pairs. And then you have the visual model. This is the 3D image of the molecule. And lastly, you have typical angles between bonds in that geometry. So in the 2 electron group, you only have 1 geometry, which is linear. Here you have a central atom that has 2 bonds and 0 lone pairs. The AXE notation is AX2E0, and the molecular geometry is linear. Okay, and of course the bond angle is 180. Next, we go to the electron group 3. You can have 2 types, 3 bonds and 0 lone pair. That is a trigonal planar. However, you can also have 2 bonds and 1 lone pair. That's 2 plus 1 equals 3. That's why it's under electron group 3. So the AXE notation would be AX2E1. The molecular geometry is a bent shape. Next, in electron group 4, you can have 3 types. You can have 4 bonds in a central atom and 0 lone pair. That is what we call a tetrahedral. You can also have 3 bonds and 1 lone pair. That is a trigonal pyramidal. And you can also have 2 bonds and 2 lone pairs. That is a bent shape. Now, under 5 electron groups, you have 4 types. You can have 5 bonds and 0 lone pair, that is what we call a trigonal bipyramidal. 4 bonds and 1 lone pair, that is a seesaw. 3 bonds and 2 lone pairs, that is a T-shaped. And 2 bonds, 3 lone pairs, that is what we call a linear shape. Under the 6 electron group, you can have 3 types. 6 bonds, 0 lone pair, that is an octahedral. You can have 5 bonds and 1 lone pair, that is a square pyramidal. And lastly, you can have 4 bonds and 2 lone pairs, that is what we call a square planar. There's no shortcut in knowing this. Unfortunately, most of the time you have to memorize it, or at least familiarize yourselves with the molecular geometry. So how do we predict molecular geometry? I will teach you 3 steps. Number 1 is to draw a correct Lewis structure, which we already studied.
I've told you this before.
Step 2 is to count the electron domains around the central atom. Now again, each region of electron density, may it be a bond or a lone pair, is counted as one domain. Remember, you only count those domains attached to the central atom. And step 3, you use the total number of domains to decide the electron arrangement. Let's have an example. For example, I have carbon dioxide. Step 1 is to draw the Lewis structure. Okay, so let's recall. Step 1A is to count the total number of valence electrons and choose the central atom. Carbon is in group 4A, so it has 4 valence electrons. Oxygen has 6 valence electrons because it is in group 6A. You have 2, so basically you have 12 valence electrons. So the total valence electron is 16 valence electrons. Carbon is less electronegative than oxygen, so it will be the central atom. So I have something like this. Step 1B is to connect the atoms with single bonds. Now remember, each bond will use 2 electrons. You're putting 2 bonds, so basically you use 4 electrons. So you have remaining 12 valence electrons. Step 1C is to complete the outer atoms first. Oxygen here already has 2 electrons from the bond. You need to make it 8, so that would be 3, 4, 5, 6, 7, 8. You use 6 electrons, subtract that from the remaining, so you have 6 electrons left. Now, this oxygen has 2 electrons from the bond. You need 8, so that's 3, 4, 5, 6, 7, 8. You use 6, so you have 0 remaining. You use 6, so you have now 0 electrons. And last, you check the central atoms octet. This oxygen has 8. This oxygen has 8. However, this carbon has 4, 2, 4. It needs to have 8. So what will happen is that these electrons from the oxygen atoms will be converted into a bond, forming a double bond. So that's the Lewis structure of carbon dioxide. Now next step, step 2, is to count the electron domains around the central atom. Remember, single bonds or double bonds, triple bond, lone pair, they are one domain. So here you have 1, 2 electron domains. Specifically, you have 2 bonds and 0 lone pair. So if we're going to write the AXC notation, that would be AX2, E0, or simply AX2. Step 3 is to determine the molecular geometry. So we have 2 electron domain. From our table, we only have 1 type, that is 2 bonds, 0 lone pair. So carbon dioxide has a molecular geometry linear. Let's have another one. Let's say we have ammonia. First step is to draw the Lewis structure. The total valence electron is 8, 5 from nitrogen, 1 times 3 from hydrogen. Hydrogen could never be a central atom, so the structure looks like this. Central atom is nitrogen with 3 hydrogen atoms. Now you have to connect them using single bonds. By doing that, you will use 6 electrons. So you have 2 valence electrons left. And then you distribute it to the central atom. Step 2 is to count the electron domains around the central atom. So you have 1, 2, 3, 4. So you have 4 electron domains. Specifically, you have 3 bonds and 1 lone pair. Step 3 is to determine the molecular geometry. We're going to check the table. For electron domains, you have 3 types. We're looking for 3 bonds, 1 lone pair, and we have this. So ammonia is trigonal pyramidal. Now let's identify the molecular geometry of water. First, to draw the Lewis structure, total valence electron is 6 from oxygen, 1 times 2 from hydrogen, so you have 8 valence electrons. The central atom is oxygen because hydrogen cannot be a central atom, so we have this. And then you connect them with a single bond. Each bond uses 2 electrons. Basically, you use 4 electrons, leaving you with 4 valence electrons. Last step is to distribute this to the central atom. 1, 2, 3, 4. You have 0 valence electron remaining. Step 2 is to count the electron domain. That's 1, 2, 3, 4. Specifically, you have 2 bonds, 2 lone pairs. If we're going to check our table, that is a bench shape. So remember, lone pairs have strong repulsive forces, so they will push the electrons to have a structure like this. So in 3D, it looks like this one.